Alright, ladies and gentlemen, welcome to the video notes for Chapter 5, Section 2 in your pre-calculus textbook, which is all about verifying trigonometric identities. This will be one of two videos that we're going to do on this. The first video will cover the how-to portion of the notes, along with a couple of examples. And then the second video will simply consist of more examples, including most of the harder examples. So, when we are verifying a trigonometric identity, what we are doing is we are proving that both sides of an trigonometric expression or equation are equal for all values of the angles involved, which means we're basically going to have an equation, and our job is to prove that that equation is true. Now that's going to require the skills that we developed in the last section 5.1. The overall basic approach will be that we will choose the more complicated side of the expression. Then we will simplify that side using the skills that we practiced in section 5.1, things like adding fractions by getting a common denominator, multiplying, all those different things. Multiplying by conjugates, we've got factoring, there's all sorts of different approaches we could use, as well as substituting in our basic reciprocal quotient and Pythagorean identities to simplify the expression. And we know, this is the advantage of this, is in 5.1 we didn't really ever know that we were for sure done. Well, in 5.2 we will know when we're done by noticing that the side that we chose is equal to the other side of the equation. So for instance, here's our first example. It's a very simple one. So we're going to go through this here. We ask ourselves which side is more complicated. Well, clearly the left side of this equation is more complicated than the right side. So we start by writing the left side of the equation. Notice I wrote LS for left side, which is cosecant squared minus 1 over cosecant squared. Now, we should recognize that cosecant squared minus 1 is one of the forms of our trigonometric identity that says cotangent squared plus 1 equals cosecant squared. If we move the 1 to the other side of the equation, we should realize that cosecant squared x minus 1 is equivalent to cotangent squared. So we're going to start this off by replacing the top of our fraction with cotangent squared. Now when we get to this point, there are no more substitutions to be made. There are no more things we can add together or multiply or FOIL. So what we should do is default to our last chance resort, which is to turn everything into sine and cosine. So cotangent squared, cotangent is cosine over sine. So cotangent squared would be cosine squared over sine squared. Cosecant squared, well, cosecant is 1 over sine. So cosecant squared would be 1 over sine squared. Now this creates a complex fraction within a fraction. Both the numerator and the denominator are fractions themselves. And we've talked extensively about how we would simplify that by taking the denominator and multiplying by the reciprocal. Now whatever we do to the bottom fraction, we also have to do to the top fraction, which causes the entire denominator to cancel, as well as the sine squareds on top to cancel, which turns our expression into cosine squared x over 1, which is just cosine squared. Come on, pen. There we go. Which is the right side of our expression. So notice that we have written as one continuous equation that the left side is equal to the right side. And along the way we've shown all the steps necessary to transform the left side of the identity into the right side of the identity. This is how we verify. Okay, we take the more complicated side and we simplify it into the other side of the expression. So we transform one side into the other. So here's the next one. Okay, we're going to verify these examples here. Again, we need to decide which side is more complicated. The left side of number 1 is definitely more complicated, so we start there. Secant squared times cotangent squared minus 1. Okay, when I look at that, the first thing I notice is that I probably am going to have to turn everything into sine and cosine right off the bat. So my first step here would be to replace secant squared with 1 over cosine squared, and cotangent squared with cosine squared over sine squared. Now don't forget that the minus 1 is still there. Okay, we have not changed it to anything, but it is still there. Now when we do this and we multiply these fractions together, cosine squared will cancel, which leaves us with 1 over sine squared minus 1. 1 over sine squared is equivalent to cosecant squared. So we replace 1 over sine squared with cosecant squared. We still have the minus 1. And then just like in the last example, we should recognize that cosecant squared minus 1 is one form of our Pythagorean identity, and realize that that is equal to cotangent squared, which is the right side of the equation, thus ending our verification. All right, on number 2. The right side of the equation would be the more complicated version this time. So we take the right side, which is secant of alpha, cosecant of alpha, tangent of alpha, minus 1. Now again, when we have multiple trig functions written right next to each other like that, and by the way, alpha is just a variable like theta or x or y, feel free to replace it with a different variable if alpha bothers you. We should realize that when we have these things right next to each other, they're being multiplied together, and our first step should be to turn everything into sine and cosine. So secant is 1 over cosine, cosecant is 1 over sine, and tangent is sine over cosine. Don't forget that there is still a minus 1 attached. When we multiply those, the sines will cancel out. And when we multiply them together, we will get 1 over cosine squared, and then we still have minus 1. Well, 1 over cosine squared, that would be secant squared minus 1. And just like on the last one, we should recognize secant squared minus 1 is one form of our tangent squared plus 1 equals secant squared. Pythagorean identity, which means we have shown that the left side is equal to the right side, and we have verified that identity. Okay, so now these do come in varying levels of difficulty. Okay, some of them are going to be harder than others. Okay, so here's an example of one that is a bit harder. It's actually fairly significantly harder. So again, we ask ourselves, what is the more complicated side? And hopefully we would all come to the realization that the right side of this identity is far more complicated than the left. So we're going to start off with the right side of this identity. And I am going to put parentheses around the denominator so that we don't screw up and accidentally do something we're not allowed to do. And the other thing I'm going to do is I'm going to provide lots of space. And the reason for that is our first step here should be to get a common denominator. Now notice that the only difference between these denominators is one is a plus and one is a minus, which means they are conjugates of each other. You may remember conjugates from dealing with radical expressions and imaginary numbers in Algebra 2. So what we need to do is we need to multiply the first fraction by the denominator of the second fraction, cosecant x minus cotangent x, both bottom and top, to get a common denominator. And we need to multiply the second fraction by the first denominator. This will get us a common denominator. Now it's worth noting that that common denominator can be simplified if we FOIL that expression. So here's some side work, okay, to show you what I'm going to do here. I'm going to multiply cosecant x plus cotangent times cosecant x minus cotangent, because I want you to see this. This is something you should do in these situations. So we would FOIL that. Cosecant times cosecant would be cosecant squared. Cosecant times negative cotangent is negative cosecant cotangent. Cotangent times cosecant would be positive cosecant cotangent. And I'm running out of space, but cotangent times negative cotangent would be negative cotangent squared. Notice that those middle terms cancel out and leave me with cosecant squared x minus cotangent squared x. This is my new denominator. Okay? So when I multiply these expressions together, here's what I get. My new expression will be cosecant x minus cotangent x over cosecant squared x minus cotangent squared x plus cosecant x plus cotangent x over cosecant squared x. I screwed that up. Cosecant squared x minus cotangent squared x. Again, the point being to get a common denominator so that I can add these numerators together. Now, when I add the numerators together, cosecant plus cosecant is 2 cosecant x. Negative cotangent plus cotangent drops out of the equation. So I'm left with 2 cosecant x over cosecant squared minus cotangent squared. Now, at this point, there are two possible ways we could finish this identity, and it's about to get a lot better really quickly. So what I'm going to do is I'm going to use a Pythagorean identity here. I'm going to replace cosecant squared with its Pythagorean identity equivalent of cotangent squared x plus 1. This will give me the expression 2 cosecant x over cotangent squared x plus 1 minus cotangent squared x. Those cancel out. Leaves me with 2 cosecant x, which is the left side of the verified equation. And we're done. Okay, so I believe, that is where we're going to stop the first video. The next video will contain the rest of the examples from your notes. Just more examples of me verifying trig identities so that you can watch them happen. Thank you very much for your time and attention.